We'll start now. So today is our third lecture, and I think the date is 18th of August. Just a quick recap of what we are trying to do and the way that we are trying to look at the problem. So in the initial set of discussions, what I tried to motivate was to describe the quantity of interest, and the quantity of interest is what you call fields. I have already defined what you mean by a field, and specifically these fields are also vectors, and that is the concept or the quantity that we are after. In order to mathematically describe it, we introduce the idea. This is what we did to a large extent in the last class. Introduce the concept of vectors. And right now, the way we are thinking about it, we are just trying to describe the field. We are not trying to do anything more than that. We are trying to get to a mathematical representation that allows us to capture this quantity of interest. While defining this concept of vectors, and I did it in two ways, but most generally what you can think is that there is this notion of coordinate system. And what you're trying to do is you're trying to look at the or mark the location of a point. And in doing so, you're asking or raising two questions. And these are how far. As soon as you say how far, you have to say from where. And then in which direction. And then this question about which direction is what brings in the vector concept. So we typically, what we do, we identify a point which we call it the origin of the coordinate system. There are some properties of the coordinate system that I'm not getting into, but these are orthonormal and things like that. That if time permits and if there is a requirement, we can talk about it, but it would not really help in the kind of things that I am trying to discuss right now. And then what you do is you mark the position and also the direction, of course, where via this shorthand notation, which I write as this R vector. And this R vector, you could do it in any way, but I'm just trying to bring in some other ideas also right now. So this R vector basically describes, let's say the position of this point is X, Y, and Z. You reach there. So it's a certain length in the X direction. So we also need to mark our coordinate system. So you move a certain distance in the X direction. So as soon as I say in the X direction, we need a way in which we would like to capture this direction. And we do it by assigning to it a unit length. So X is the magnitude, that much in the direction, and the direction is specified by a unit vector, plus Y in the Y direction, and plus Z in the Z direction. So this would be a location of a point. Also realize in doing so, the three numbers X, Y, and Z, now we are capturing it via this single notation, which is R. And that is a simplification that by going to vector algebra that you introduce a mathematical simplification in the problem. Most generally, any vector, so let's call it an arbitrary vector A, you can think about it in terms of its component, which I call A sub x in the x direction, its component or magnitude in the y direction, and its component in the z direction. So we have talked about these things. Now, having got to a representation of this vector, and we are still not talking about fields in general right now, I'm only in the domain of vectors. We said what operations are possible, what mathematical operations are possible. And I talked about in the last class about addition, subtraction, which is in principle a type of addition only. And then the third was multiplication. You can look into the details of these. I have tried to give you a general idea when it comes to addition. I have talked about those properties, that it is commutative, associative, talked about subtraction. If you want, you can take a look at the law of cosines and things like that. All those are there, but let me not try to derive those things. Where I said that things become more interesting is this idea of multiplication. And when one thinks about multiplication in vector calculus, you could have a scalar multiplication. Scalar is just multiplying by something which is scalar. Then you could have operations which involves two vectors. The first one is dot product, and the second one is cross product. Then what I tried to do was I tried to get into a little bit of the details of the dot product. So typically when one thinks about dot product, you have two vectors, vector A and vector B. And when you are taking the dot product, what you are doing is you are multiplying the magnitude. So these things I am assuming I have talked about that, but how you get the magnitude and what you mean by magnitude, I assume that this is well known. So you basically have the product of the magnitudes and then the cosine of the angle between them. And the right hand side, there is no direction associated by it because you have a product of just simply three numbers. Cos of an angle is a number, the magnitudes are themselves numbers. So this is a scalar quantity that you obtain. After having said all these things, I said that let us try to now get into the component form because we are really thinking of a three-dimensional space. So it would make sense to think about all these operations in three dimensions, and also given that we are worried about these quantities which are fields in themselves, it makes sense to think about them. So then I said if you have two vectors, so let's say vector A, as we have written in the previous page, we can write like this, and similarly vector B. We can write like this. So when you take the dot product, realize that the new ingredient that comes in is that you need to know how these unit vectors they do these operations, right? Otherwise it's just the product of the numbers. In order to do that, what you need to know is, for instance, what this dot product is going to be. And given that you're working with an orthogonal coordinate system, and given the definition that we had earlier, which was the magnitude times the cosine of the angle between them, we know that the magnitude is 1. We are thinking about unit vectors, and then it's the cosine of the angle, which is 0, which is essentially 1. So you can immediately, and all these things, I hope they are pretty well known to you. All these would be 1, and any other a dot product which involves the two different axes, there would be 0. So these are things that we know quite well. Having this information allows you to write the product immediately in the component form. So all that you are doing is you are multiplying the magnitude and you are looking at the vector operation on the unit vectors. That is what you are doing. And it's multiplication component wise and then adding them. That is essentially what comes out. And given two arbitrary vectors A and B, most generally, this gives you the dot product. Then what I did was, towards the end of the last class, I said that, of course, we also realize that if you were to take the dot product of a vector with itself, what you will get is the square of the magnitude of the vector. And I raised the following question, that when we started this entire discussion about physical laws, I talked about these physical laws. One of the important aspects to that is that a law is a physical law. If it is invariant, there exists symmetry, it is invariant under certain operations. And I said, is this operation invariant? Is the dot product of a vector with itself, is it invariant? And the answer, of course, is going to be yes. This operation is certainly invariant. By invariant, what I mean over here is that you have a number on the right hand side, you have a length on the right hand side, call it a step length or something like that. Irrespective of whether I slide my coordinate system or I rotate it, the length of the number cannot of the vector cannot change. There is no reason because of which it is going to change, and hence it is going to be invariant. So remember that we are trying to represent physical laws in terms of vectors. Physical laws should possess some properties, and the question is do these vector operations, they have the same properties? And then there is a counter to that anything which translates and rotates in the same way as a vector does, then it is also going to be a vector. So all these concepts are inbuilt into that. Finally, what I tried to do was, or maybe I didn't raise this question, is if I have these two vectors, A and B, and I take the dot product of them, is this going to be invariant? That's a reasonable question to ask. We're talking, still it's going to be a number, and you can say that yes, this is what it is, or you may say no. But realize, I'm not trying to ask it to you, but think in the following way, that if I construct a vector C, which is vector A plus vector B, and then I take the dot product of C with itself, I know that this is going to be something which is invariant. And on the right hand side, what I need to do is I need to take the dot product of this sum of these two vectors. What that will give me is A dot A, which is the magnitude of A square, magnitude of B square, and then there will be a dot product that remains. So this will be A square, this B square, A dot B. Now realize we just argued that this magnitude is certainly invariant. The second is also just the length of a vector. It's invariant. So finally, what you can say is what remains on this right hand side is A dot B, and what is on the left hand side is the dot product of a vector with itself, which is really the magnitude of the vector C, which is certainly invariant, and hence this A dot B is going to be invariant. Why I am trying to raise this point? So think about the following problem. Let's say you have a two-dimensional, or you're thinking in terms of a plane. So let's say we have, so I'll just draw the axis here. You have y-axis and x-axis. And in this plane, you have a vector B and a vector A. And let's say that the vector A is along the x direction, and the vector B is in some direction in the plane. And the angle between them is going to be theta. So if I were to do this component form, dot product of these two, this would be the A vector, which has only one component, that is along the x direction, and the dot product of this arbitrary vector B in the plane. And based on what we just did, you can easily show that this is the product of the magnitude of the two vectors along the x direction, which I can write. So AX is the magnitude of vector A along the x direction, and BX is the magnitude of B along the x direction, which I can write from this figure that we have. So just drop a perpendicular on this line. So the component of B along the x direction, that is simply going to be whatever that magnitude of B is, cosine of theta. Or since A is only in the x direction, I'm going to drop this x and I will write it as AB cos theta. So in this simple, very straightforward example, what we have obtained is something that we started with, and then we went into the component form, and something that we knew very well, which is the dot product of the two vectors is A times B cos theta. But had these vectors been placed in any arbitrary way in this coordinate system, knowing very well that this operation is going to be invariant, the right hand side, it better be invariant. So they could have been placed in any way. You do not really need to place it in such a nice way and bring the formalism out based on that. It's a completely general idea. So now I hope that you understand that this writing in terms of dot product, it brings into that property that this operation is going to be invariant under translation, under rotation, and these kind of operations. Where does this really come in? Where do you quite often see this dot product? So you may also try to now ask the question that where does one see all these things? And one of the places that you quite often see this is in the calculation of work done. So let me try to take up a slightly physical example. So let's say you want to calculate work done, and the work done is defined as it's the rate of change of kinetic energy. So let's say that I write let's represent the kinetic energy by this notation T. You can write it as most generally as half mv square, but now you are thinking in terms of components, it's the dot product of the velocity with itself. If you want to calculate the rate of change, okay, and rate of change I have not defined, I'll define later, but we all know what a first order differential is. With time, I can write it as half m by dt dot v plus half m v dot dv by dt, which I can write as m dv by dt dotted with the velocity. Now realize that this quantity that we have written over here, that is nothing more than the force. So this I can write by representing force as some vector f. It's a force being applied in some direction. And now if you think about work done, I'm going to define work done, all these things at the right places, but I'm just trying to give you an idea of how the dot product becomes useful when you're trying to describe such kind of systems. So to calculate work done, what you do is the rate at which the kinetic energy is changing, you integrate over some time. So this, for instance, could be from 0 to some t prime, which by putting in this rate of change expression that we have just obtained, you can write as f dot v dt. Now this velocity vector v, you can again write it as the derivative of the displacement. So let's call it some ds vector, which finally gives you f dot ds, the force, the dot product of the force with the displacement. And you have seen such examples before. One of the classic examples that you have seen is that you have some sort of, let's say, inclined plane, and then there is something that is falling under the action of gravity, and you are interested in calculating the work done. And realize, since it is in the under the influence of gravity that it is falling, so gravity has a certain direction, this force has a certain direction, that's downward, and the motion has a certain direction. And what this expression is telling you, the inclined path that is there, it could have been in any possible way, it doesn't really matter. All that you are concerned about is, remember this dot product that I talked about, a dot b, then I said it's the projection of b in the direction of a. In the same sense is the projection of the displacement in the direction of the force that is there, the gravitational force that exists. So all that you are concerned about is that particular projection, and you're done. You do the integral and you're done with the problem. It's in formalisms like this, and it's a very neat concept in itself. It doesn't really. So for instance, if the motion was perpendicular to the gravitational force, will there be work done due to this force? Then the answer is no, because you have a dot product. The projection is simply going to be 0. So all these things are naturally inbuilt into such kind of descriptions. Okay, so I think you get the basic idea about how to do these calculations and where it comes in handy. Okay. As far as the things to make a note of are concerned, remember that whenever you are going to operate two vectors, you need to know how this operation is carried out within this unit vectors, okay? The elemental building blocks, if you wish. And this is going to be extremely important as we get into more involved concepts from here. So this is all about dot product, and dot product has to do with calculations about work done, and it is, you can think about it as projection of one vector in the direction of the other, and things like that. The other operation that you need to know, that is what you call the cross product. Typically, when one thinks about cross product, one immediately gets into the idea of calculating areas of a parallelogram. Again, something that I'm not going to go into, but the cross product of two vectors, it is defined as the magnitude, the product of the magnitudes, times the sine of the angle between them. And then there is a direction associated with it, which is represented by this n with that hat on top of it. So that's a unit vector signifying the direction of the dot product. And typically what you have is, in order to, so you're looking at a plane, you're looking at some surface. Let's say you have a parallelogram and you're trying to calculate the area. So anytime you try to do that, there are two possible directions for this area. And the straightforward way is that you start from the first vector, you curl your hands towards the next, and the direction in which your thumb points, that's the right hand thumb rule. That's the direction of the cross product. But what we are also interested in at this point of time is the component form, because we are going to think in terms of all these fields, fields in space and things like that. So taking off from something that I discussed in the context of dot product, you know, in order to do this operation in the component form, what you will have and now in order to complete this entire operation, you need to know how does that operation carry on when you involve these unit vectors. And I'm not going to say a lot of things here because I think it is sort of straightforward, but you know, when you are looking at the cross product of a unit vector with itself, it should give you a 0. The sine of an angle between them, and it is just going to give you a 0. It's the other ones which become important. So you have the cross product of the unit vector in the x direction and the y direction. That will give you the unit vector in the z direction. And this will give you the so if you have the unit vector in the x times the unit vector in the z direction, this will give you a negative of the unit vector in the y direction. So there is a cyclic thing if you want to just reduce the workload. So it's x, y, z. So you can think it, so the direction of the arrow basically is the positive sign. So if along the cross product is along the direction of the arrow, you take a positive. If it is in the other way, you take a negative. Then the other two would be and again, once you have done this, however lengthy the calculation might look, you are essentially done as far as the problem is concerned, and now you can very neatly write it as. So now using all these things, you can write the cross product as. So let me write it over here. You are going to have. I'm just doing a mental calculation. We all know the answer to that, but the objective again was to show you how the operation carries forward. So this is AY BZ minus AZ BY plus Y direction AZ BX minus AX BZ plus Z direction, and you have AX BY minus AY. Okay, and this is it. But there is a much more simpler way in order to do that, and that is also something that it is possible that we are all used to. That the same thing, now you can think in terms of a determinant where this A cross B would be equal to, again we all know how to calculate determinants, x A y A z B x B y. And this is what it is. This is the final thing. Again, I'll repeat this again. This will certainly be useful when we'll talk about how the vectors, how to write them in different coordinate systems. This concept or this idea will certainly be of use over there, that when you are doing vector operation, think in terms of the how the unit vectors, when you do the same operation on them, what is going to happen. It's going to be extremely important over there. So now we have the basic template laid out. What we have talked about is that we would want to describe this field at some location in a completely arbitrary way, and the notation, the representation for that is going to be in terms of vectors. We want to know how things would add. We want to know how certain kinds of operation will take place. I also talked about, and later you will see that why these operations are coming in. So if you recall, I specifically said there are two special properties of these vectors that would be of interest. And these have to do with things, this concept of flux, and then this concept of circulation. Okay, how much crosses a surface versus the circulation along the line. And these are the two most important concepts that are there when it comes to describing this electromagnetic fields. Okay. So I think the basic thing is well laid out. We know how these vectors operate. We know how to work around with them. So let's move forward from here. You will see some questions related to these ideas in the tutorial. So I'm not going to spend time on this. These are the same things written. You may want to think about, this is already said, that if you have a cross product of a vector with itself, what will happen? Also, if you have a dot product of a vector, so vector A, the dot product of that with the cross product of vectors A and B, then what is going to happen? Again, usually when you pose these problems, you want others to think, but realize that this vector, the direction of the two, the direction vector, this n vector that I talked about, that is really perpendicular to the plane containing the vectors A and B. So if you are thinking of the product of these two vectors A and B, and let's assume that A and B both lie in the xy plane, then the direction is going to be either positive z or negative z, depending on how they are laid out. But if vector A is in the xy plane, and the outcome of this operation is going to be in a direction which is orthogonal to the xy plane, then what is going to be the outcome of the entire operation? So you may want to think about it. It's a straightforward question. I'm on purpose not giving the answer, but I have given you what you want to do in such a situation. I did talk about representing of these vectors, the sum. So these are things that I've already talked about. These are just slides which capture the same idea. It's the same way of looking, as I said, that you move a certain length in the x, then a certain length in the y, and finally a certain length along the z direction. And that is what you mean when you try to describe these vectors. And from the origin to the point of interest P, you typically, and this will I'll mention in a moment again, you represent it by a vector which you write as either the scriptor or the other one. In fact, this one. So this is the right notation for that. Okay, this is something that is, so the vectors that are important, and you should certainly know what these vectors are. These are your position vector, which is the position of a point, and this I have already defined what it is. Unit vector, which is the position vector divided by the magnitude of the position vector. Again, something which we have used, which is very quite important in our description. small length. So realize also the notation here, I am using bold for vectors over here. So this is really a small length infinitesimal displacement vector, which is, I wrote ds when I talked about work done. It's something similar to that. It's a little change in the x, little change in the y, slight change in the z. And then another vector is the, basically is the difference of two vectors, but it is the typically what happens that you have a source and then you have a point of observation. So you mark the position of the source with one vector and the observation point, and then the entire operation is in terms of the separation vector. The separation here is between the location of the source and the point of observation. So that is where it comes in handy. So again, these are straightforward things. I'm not going to invest time into these, but you should know that these are the vectors. So later, when we talk about the different laws and these come, it should not surprise you. Dot product, cross product, I've already talked, so let me not get into it. You can do more operations. Okay, these are again things that let me not spend time on it, but you may want to at least for once derive some of these things for yourself when you're reading the text or even otherwise. And it has to do with scalar triple product. And by the this triple product is essentially everything. So beyond this, even if you have more vectors involved, you can always break it down into this triple product or even lower than that. So two which you may want to know or at least look at is the scalar triple product. Scalar triple product has to do like the cross product was the area of a parallelogram. So now you're including height also in that. So that's now a volume. So you can just simply think of it like that. The determinant notation, I've already talked about it. You can simply calculate if you know how to calculate these determinants. Then you can also have the vector triple product. The first one, you can remember it as the BAC minus the CAB rule. So it's A cross B cross C equals, it's a vector, it's a cross product. So it's the dot product of A with C, and then you multiply it with the, so that's a scalar, and then you multiply it with the vector B. And then you have the dot product of vector A with B, and you multiply it with the vector C. You can also try to see if these things you can prove. I'm not going to get into it. A cross B cross C is equal to negative of C cross the cross product of A and B. So this is the elementary part of vector algebra that one needs to know. These operations one should be aware of if you want to move in and start doing other kinds of computation. But what kind of calculus or what kind of stuff would we want to do? And the objective now, so the first level description for the first level task was to come up with a description of these fields, and that we said it's in terms of the vector field. But remember that we have already talked about that these fields are going to be everywhere. That's the idea. I said this is a force waiting to happen. You once you put the probe, you see a force. So that force waiting to happen is called a field. Or in when I define fields properly, I said field is a physical quantity which takes up different values at different positions of space. So there's a variation in space. And mathematically, the moment you try to describe such continuous variations in space, for instance, you do two things. You take derivatives and or you do integrals. The most important part in our entire description, and this is the part that one has to be very comfortable with in order to get into the physics aspects of the course, is the vector differential calculus and the vector integral calculus. When it comes to vector differential calculus, and these will become clear as we move along, the concepts that are of important or the operations that are of importance are gradient, divergence, curls, and some higher order derivatives. When it comes to integral calculus, typically you always think in terms of just single variable integral. Maybe a surface is what you would have seen, but here since it is vectors, So there's a line integral, there's a surface integral, and then there's a volume integral, but all in terms of these vector fields that one is thinking about. So the next part of what I'm going to discuss is now going to focus on all these different things. So let me start now with vector differential calculus. And just a moment back, I said that the objective is to describe the continuous variation in the fields. So let's say, I think very simply in terms of one dimension, that you have a field which you can describe as some function of x. If you want to put a picture to this, so it takes up, based on the value of x, it can take up different values. So this is f. And the task is the following. Let's say at the position x1, you know what this f of x is going to be. Typically in a maths course, what happens is this f of x is known to you. But that is not what we are saying over here. We are just trying to describe it in terms of some function. And if I went to some other point, let me call it x2, I'm interested in knowing what this f of x is going to be. More specifically, if x2, so let me first say let x1, doesn't really matter, but so x1 I'm going to say it's some x, and x2 is a point which is not very far away from x, and I am going to write it as x plus delta x. So my job is to find the value of this function at the location x plus delta x in terms of this f of x, okay, plus whatever. So this is just for completeness over here. If the curve, if f of x is a straight line, then everything is very well known to me, because what I know is f of x would be equal to, this is the equation for a straight line where m is the slope and c is the intercept, and these things are known. So I can write x plus delta x, this delta x plus c, and then either I can calculate, knowing what this delta x is for the straight line case, of course, this fx plus delta x, or many times what we are interested in is really the change. So the change in the value of the function between the two locations, and let's represent it as some, let's not put a d, let's call it some delta f, which you can immediately see that that is nothing other than the slope. But this is true in the case of a straight line. You would like to do it most generally for any kind of function over here. And you may yourself try to see that if instead of f of x being a straight line, if f of x goes as x squared, let's say, then where the problem will arise and things like that. Again, without deriving these things, because that is not the intention of this course, a formalism that allows you to do this is what you call the Taylor series expansion. in the most general way. So I can expand f of x plus delta x via what you call the Taylor series without deriving these things. And the way it goes is value of the function at x, which is the known part, plus delta x times the derivative of the function f with respect to x, plus you will have the square, and realize all these terms, if delta x is extremely small, all these square and cubic and all other terms, they are going to become, the magnitude is going to become smaller and smaller. And the other assumption, of course, is that these derivatives, and we have some idea about what derivatives are, these higher order derivatives as you are taking up, there is no discontinuity or anything like that happens. So the function has to be well behaved, and all those mathematical properties are true. So you can write like this, and very simply, which is exactly true for the straight line equation, you don't worry about all these higher order terms, and you write it as okay. And finally, you have everything. So you can write this delta f, which we defined as f of x plus delta x minus f of x, divided by this quantity delta x, to be approximately the same. And by approximately, I mean that you are allowed to ignore the higher order terms. And this becomes better and better in the limit that delta x becomes smaller and smaller, and mathematically you say that it tends to 0. So essentially, this operation, which is the derivative of the function with respect to the variable, what it allows you to do is it allows you to get an estimate of how fast or slowly the function is varying. So the change in the value of the function with respect to the change in the variable, it gives you an estimate of how strong or weak that change is going to be. And this is, we have done this, we have seen this in the context of a function which depends on a single variable. Right? So that is the basic idea of derivatives, and that is why you encounter these derivatives almost everywhere. If you recall your Newton's equation of motion, where the variable is the time, you say that the rate of change of position with respect to time, you call it to be the velocity, and then the rate of change of velocity with time, you call it the force divided by mass. Right? And that is the idea of derivatives. You are just incrementally changing things, and you are asking the question, by how much has the quantity of interest changed, whether it's position, whether it's velocity, or it could be something else. So all these are in a mathematical sense tied together. But our job is much more than this. It's just not about functions of single variables. So now, if I were to ask you about, so let me put it like this. What about three dimensions? Because recall, we talked about the description of fields, vector or scalar, but we are thinking about the scalar functions for the time being. That in terms of the variables x, y, and z, and it's for a particular instant of time that you are trying to look at it, temperature and all these things being a classic example. So now the space is just not this one axis, which is the x-axis. The space is the entire 3 dimensions. And what I would like to know is how fast the function is changing with respect to a step that I take. I can move in some direction and the value of the function is going to change. So let's say that you are able to think in terms of temperature, for instance. So the temperature, typically the way you draw is, so some value over here, some other value over here, and so on and so forth. And if you were to take a step, right now you're over here, such that the temperature has some specific value, you take a step in some direction. What is the change in temperature going to be? And temperature is a scalar field over here. So like earlier, I can still go back to the idea of Taylor series expansion with only one more thing added, and that is now instead of a single dimension, I have to worry about 3 dimensions. So that is all that I have to worry about. So like the previous question, our intention is to calculate the value of this function when you change position by a little bit. Again, using Taylor series, you can write this to be equal to value of the function. This is the exact same way in which we addressed the previous question, at the location xyz plus, now you're thinking in terms of 3 directions, a small change in the x and how much the function changes in that direction, keeping the other 2 values to be constant, plus the other one. So now it's just the terms being repeated. And then you have higher order terms, which I'm not writing. We know that it's a first order, the linear part that we are only going to worry about. We don't want to bring these squared and cubic terms and things like that. Again, in the same way, like I just mentioned, I can bring this f, or the value of the function at the location xyz, to the left hand side, and I'm going to call that change to be some df, delta f if you wish. That would be approximately equal to, I'm going to drop the higher order terms. So this is just f x plus delta x, y plus, so slight change in the location, minus f at xyz. So that is what this df is. And this is delta x So this is all right. This is under some assumptions, which allows us to make some approximations. We obtain something like this. We'll just rewrite in a slightly different form by identifying that what you have for each term is a component-wise multiplication of 2 vectors. And it will become, if the statement is not clear, the operation will become clear quite soon. So what we are going to use is, let's say that you define a small length vector, which I call to be dl. This is the infinitesimal displacement vector, which, if you recall, we wrote as dx in the x direction plus dy in the y direction plus dz in the z direction. The other vector that I'm going to define is my derivative vector, but now, or the derivative, but now as a vector, which I'm going to write like this. Okay, this notation I will define. So this is what you call the nabla operator. And we are going to define it like this. the derivative of the function with respect to x in the x direction plus the derivative of the function in the y direction with respect to y, and then in the z direction with respect to z, the derivative. Realize that, let me go back one page, that this df that I have written, which is delta x derivative of f with respect to x, and this is a partial derivative. So let me not assume that this is known. So this is a partial derivative. It's not a total derivative. It's a partial because you are only looking at the change in one direction. You are not looking at the change in all the directions together. And you are accounting for the change in all the different direction by having all these different terms over here. Okay, so realize that this df that I had, that can be written as the dot product of these two quantities that I have justified. The first of these is the infinitesimal, call it displacement, call it line element, whichever way you want to think about it. And then there is the other one, which I'm going to name it in a moment. But I hope that what you realize is that this, writing it in this form, if you open it and write it, it will exactly give you the quantity that we have, which is, I think I changed the notation a bit, which I should not have done. So this, I'm taking the, I'm sorry, in the flow I sort of missed. So I'm making this delta x, delta y to be very small, and I'm calling it to be dx dy. So that's the change in notation that it just happened. I did not think about it.
Sir?
Yep.
Sir, what is...
Go on.
Sir, what is difference between delta x and dx?
Just think of it as delta x becoming very, very small. That's all. So delta x would be any change. So think in terms of a scale. The scale here, for instance, could be a centimeter scale, and delta x could be 1 centimeter. So that's a discrete thing. In order to make things continuum, the assumption is that these points are very not separated out by a lot. So let's say the separation is just a micron. So x is equal to 1 centimeter plus 10 raised to minus 6. And that you mathematically represent as this differential dx. So that's the only thing. It's nothing more than that. So in
what is difference between dx and del x?
Yeah, that's what I said. Let me go back. So this notation del x and dx, right? This is what you are talking about. Is that correct or no?
No, sir. Delta x. I think written df upon dx you have written here. No?
This guy.
Yeah.
That's a partial derivative.
Partial derivative. So what is the partial x? Difference between partial x and dx?
Okay. It's the same. So the way that you want to think about it is the same as you would think about this delta x and dx. That partial notation just comes because it's a derivative of a function which varies, which is dependent on different variables, but you're taking the derivative only with respect to one variable. So that is why that partial notation is coming. If you look over here, there was no partial notation over here. This was in single dimension. That's point number one. So don't get confused with the partial part right now. All right. The second is why this delta x being written as a dx thing. And the idea is quite simple, that delta x right now is any arbitrary change in x. But mathematically what you do is when you say this is very, very close, so you write it as a differential. So that differential notation brings in the d instead of the delta. So that's the only thing. So I could have, at this point, for instance, I could have said that this delta x, now my assumption is going to be that it is something which is, the increment is very, very small, and hence we are going to write as dx. So that's the step that I did not mention. That's the only thing, nothing more than that. Is it clear or no? Okay, think about it. It's not, so it's just rewriting it in certain way, but with the assumption. So from this to the next page, the assumption is that limit delta x tends to 0, delta y tends to 0, and delta z tends to 0. That's all that we are doing, nothing more than that. But the point that I am trying to raise is essentially that if you now define these two vectors, one has to do with the infinitesimal line element. So what you are doing is, in the x direction, a small step, very, very small step. Then in the y direction, a very, very small step. And finally, in the z direction, a very, very small step. And this small is really small, but how much small? There is no answer to that question. It is so small that instead of thinking in terms of discrete, you can think in terms of continuum, and whatever the continuum expression gives to you, that holds true. So as far as I am concerned, that is what it means, because there is no other way to put a meaning to this, how small. There is not going to be any meaning to that. But assuming, and it will be true, that assuming all these things hold true, then realize that this operation that I have tried to write over here, you can open and write it as something that we wrote in the previous page, and the only difference was that this we had written as delta x, this we had written as delta y, and since we are looking at very, very small, which is the reason why we call it infinitesimal, we are writing it in these differential notations. I hope that is clear to everyone. So it's the same thing. So what we have, and this is what I want you to think about. This is the important part of the entire exercise that I was doing. You are looking at the change in the value of the function. As you do what? Right? As you take a step, as you take a small step in some direction, this aspect is captured in the small line element. That's why it's a small change in a certain direction. So when you take this small change in a given direction, by how much the value of the function is going to change will depend on the operation that is shown on the right hand side, which essentially has three parts to it. It is a dot product, first part that you should realize. Dot product between two quantities. One is the line element, which is in a direction, which is in the direction that you are taking that step. And finally, it's a vector operation on a scalar. This entire thing, this vector operation on the scalar function f, is what you call to be gradient. Mathematically, and it will become clear as we get a little bit deeper into it, but mathematically what you are doing is, you have an operator. This operator, so let me define this operator over here. I'm going to write this operator as a vector of partial derivatives. This operator, it operates on a scalar function. Okay, that's another thing that you should remember. Just in today's class also, I talked about, when it comes to vector multiplication, if you're thinking in terms of multiplication, there are three things possible. It's a scalar multiplication, then a dot product, and a cross product. So this operator being a vector in itself, the operation that you have over here, it operates on a scalar function f. So f is a scalar function, or a scalar field if you wish, which is a function of x, y, and z in the Cartesian coordinate system. And this entire operation, you call it to be a gradient. What it gives you, so we are going to go a little bit back and forth between these things. The left-hand side is by how much the function has changed. That is the change in the value of the function. This is the, so compare this with the expression that we had earlier. So we had written the change in the value of the function. This was in one dimension. If you recall, there was no vector associated with that. And so you're looking at the change in the value of the function. So that is the left-hand side. The numerator part of it is left-hand side. As you do what? So in one dimension, you take a step in the x direction. That's the only dimension that you have at your disposal. And that there we related it to the slope in the case of a straight line, which was exact. Otherwise, if this is very, very small, then only it's going to be the slope. If that dx is some delta x, which is large, then having this representation is not going to work. So the left-hand side is essentially the change in the value of the function. Change in the value of the function as you do what? As you take a step. But now you're standing in higher dimension. It's a three-dimensional picture. So the step could be in any direction. You are standing on the top of a hill. It could be in any direction. I'm standing in this room. I could have taken it in any direction. And the objective is to calculate the change in the value of the function itself. And that is related to this mathematical operation, which we call gradient. So you're taking your direction in which the step is has been taken and project it into this onto this operator, which has derivatives in it, which has all this partial derivative. To understand what is really happening, ask the question, when is the change going to be maximum? So let us ask the following question. When will df, the change in the value of the function, be a maximum? It would be maximum when dl and this gradient of the function f are in the same direction. It's a dot product after all. What does this operator involve? It involves partial derivatives. Partial derivatives of the function f along certain direction, along the x direction, along the y direction, and along the z direction. And hence, it is a vector. So it's giving the rate of change along certain directions. That is what it is essentially giving. So when dl and this operator, they align in the same direction, or they are in the same direction, that is when df is going to be the maximum. Okay, I'll say a bit more. I don't think I'll have, I'm out of time, but I'll take up more examples, and I'm going to talk about them as we in the next class. Right now, just take it as a mathematical operation. More physical insights I will give to you. One thing that I will say, and that will, it may or may not be clear by that, but at least let me conclude by saying that thing. Let's say this dl vector, I write it as some unit vector. It's the direction of the length times the magnitude of that length. So now I can write df dl is a dot product of a unit vector, which is along the direction in which one moves. So now it's in a real sense the derivative, something that I had written earlier. It is the derivative with respect to x, for instance, in a single one-dimensional case. So it is really a derivative. And now think of the same question. So it is a derivative with respect to the length, the change in the length. The length has been taken in a certain direction. And when is it going to, so this unit vector, it gives the direction in which the step has been taken. So in which direction is it going to be the maximum? It is going to be the maximum in the direction given by this operator, which is the gradient operator. I hope you see this picture. Later when I take some examples, it might become more clear. But at least just from the operation itself, I hope that you see the point. The left-hand side is something that we very well know what it is. It's the rate of change of something. Not rate of change, it's not a time, but it's the change with respect to, it's a differential derivative, which is the change of the function with respect to some quantity. It depends on two things. It depends on the direction in which this the step has been taken, and also on the direction given by a vector operation, which we call to be a gradient. In which way is it related? It is related via this operation of dot product. What does dot product mean? Dot product means it's the projection. When is this left-hand side going to take its maximum value? When that projection of the direction in which the step has been taken is along the direction of this gradient operator. Right? So now you ask the reverse question, which is that direction? That is the direction of the gradient operator. So what does this give you? It gives you, so its direction gives you, its direction gives the value of the direction, I should write, value of the direction. No, let's not say value, let's say its direction gives the direction in which maximum change occurs, and its magnitude gives you how much. Okay. So you have a scalar field and you are asking the question, in which direction does the maximum change happens? Take the gradient of that scalar field. How much? That's the magnitude of the outcome of the gradient operation. Okay. I'll just say one or two more things which is relevant for today's tutorial. You should know that. I will discuss the concepts in the coming lectures, but at least mathematically you know. So we have defined this operator, okay, which is a vector operator. We have talked about one operation which is on a scalar, and this is what we call a gradient. You can do the same thing once you have a vector. You can do the exact same operations again. So you can have it operating on a vector, or you can have it operating as a cross product on a vector. So this operation, which is a dot product on a vector, it will first of all, it will give you a scalar. Okay. The name would be divergence. I will talk about these concepts in the coming classes. I'm out of time today, but you should know, because these things you'll be calculating in the tutorial. The way you calculate is the exact same way in which you calculate all those cross products that I have discussed at the beginning of today's class. And this one will give you a vector, the cross product of the operator, nabla operator with a vector, and it is called curl. These two operations, one of them, it measures the flux, it is related to the flux that we had talked about, and the cross one, that is related to this going around. Okay? The tendency of the vector field to curl. So these are the two operations. The operations wise, once you know the definition of the operator, once you know what the vector is, you can do quite easily. If this is equal to 0, then you say that the vector field A is solenoidal. If the curl of a vector field is 0, I'll show it to you later and put it in a proper physical picture, but from just a mathematical or a calculation point of view, just know this much. And so gradient is just more like a derivative that allows you to compute the rate at which the function is changing as you shift your location. The divergence is how much it moves out or moves in. It's a flux related quantity, and the curl has to do with the rotation. So if the curl is 0, then it cannot be irrotational, and if the divergence is 0, it is in a way rotational, but you call it to be a solenoidal field. Solenoids, I hope you know what they are. So it's the same idea. So let me stop at this point. I think I've already taken more time, but if you have questions, you can ask now, or this much you would need